So this is our session 4, in which we will be modeling and design of the strap footing for 2-story commercial building. That previous building that we modeled, the footing we modeled in the session 3. So there are 2 cases in which you can shift from isolated footing or combined footing to a strap footing. But the strap footing are normally provided with the combination of the isolated footing, right? So the first one is if there is any restriction from the client or architect or on the footing thickness due to some reasons, then you will be facing punching issue in the foundation, right? So to overcome this issue, you have to go for the strap footing. You have to provide the strap beam in between the isolated footings, right? Another reason may be to shifting from the isolated footing to the strap footing, maybe of the low bearing capacity of the soil. For example, previously we assumed that the bearing capacity of the soil is 2.1. So if it is 1.5 and you have calculated all the area that will be resisting the superstructure load, and it is less than the required, so you can also use the strap beam for the safe transformation of the load from the superstructure to the substructure, right? But let me go back to the session 3, which is the isolated footing, and I felt that there might be some confusion in the mind of some students that we haven't checked the total capacity against the total demand. But the reason why I didn't check that, because in the calculations, we calculated the area using the allowable bearing capacity, right? So if you calculate the area using the allowable bearing capacity, then there is no need to check the demand and capacity because you have already incorporated in here, right? But for the cross check, I have included that to check the demand and capacity. So our capacity was 4.63 KSF in case of the isolated footing, which we have done previously. And the total demand coming from the superstructure was 2006 kips. This is the total service load, which I have shown you how to calculate it, or how can you show it in the ETABs by defining the service load combination. And the area of the footing we have provided for the interior columns was 4 feet and 9 inches, 4 feet 9 inches, and the total was 13. If you count that, here is that footing. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, right? So total 13 footing, and the smaller one is the 24. So if you calculate the total area of the footing, which is distributing the forces, is 13 into this and 24 into this. So the total area of the footing comes out to be 630 square feet. So the total demand coming from the superstructure is this, and the total area that will resist this load is this much. So when you calculate this, it comes out to be 4.1 KSF, and the capacity is 4.6. So it is okay. Why it is okay? Because you have already calculated the area from the allowable bearing capacity, right? So this was a small check. So I wanted some of the guys have any confusion, so this will clear their doubts. So let us move towards our session 4 again. So these are the 2 reasons which may force you to transfer from the isolated footing into the strap footing by providing a strap beam in between the isolated footing, right? So we will take the previous isolated footing, footing thickness 12 inches, and keep all the other properties same. The loading criteria from the ETAB and all of these are the same, right? So this is the model, right? This is the 12-inch thickness. So there is no other issue. But if I click on this punching check, so there is a punching issue. And for some reason, the architect or the client had restricted me to not use then 12 inches thickness, more than 12 inches thickness, right? So I'm restricted to that. So to overcome this problem, if I increase the area and move towards the combined footing, so this will be not efficient, because if I combine these footings, there is a larger area in between these, and still there will be some problem in the punching, because
coffee there.
Right. So moving towards the combined footing or strap footing will not solve my problem. Somehow it will solve my problem, but it will be uneconomical, The economical is to give the strap beam in between these isolated footing. This will be economical and it will solve your issue of the punching, right? So let me unlock this and we will go towards the define for the strap beam, and we will, I have already defined that. So let us modify this. So you can write the property over here is 12 plus 15. 12 is the depth because the maximum thickness you can depth you can take is the thickness of the footing, which is 12 inches. And this is the material property, which is you can see 3000, which we have defined previously in the ETABs. This is 3 KSI, right? And all other properties are the same, grade 60 steel. And you have to select the rectangular beam because there is no continuous T beam like the slab beam. This is a rectangular beam. So this is the 12 inches at the top, and this is the depth we have to take is 12, and you have to make the width as 15, right? So the maximum depth you can take is 12 inches, right? So this is the beam, and you have want the software to calculate all the other properties automatically from the slab properties, right? So this is how you will define the straight beam, and you can define as per your requirement, and you can check the other properties and the cross-section moment of inertia and all of these, right? So this is how you will define the straight beam, and you will name it. For example, this is the beam 15 cross 12, right? So click on OK. Now go to the draw and draw beam lines. Click on this, and now you have to draw it with the center to center of the column to overcome this problem. So this is the column. So I will join this column with this column and this column, and with this column, this, right? So you have to combine all of these columns with each other and connecting these as straight footing with the strap beam, right? So this is how you will perform for the all of the footing. Similar for the interior one, right? You can draw from here to here, and you have to join it with the center of the column. So the beam is passing to the center of the column, so we do not face any punching. You can also go towards the screwed view, so it can be seen very easily, right? So this is how the screwed view will be shown. You can see that the beam is passing through the center of the column, right? This is how you will model the strap footing. Right? So this is a typical procedure which you will follow and model all of your beams in SAFE. And this is the extrude view, which will make your work very easy and efficient, right? So similar procedure will be followed for all of these. So to save the time, I have already drawn this in this model. This is the same model. And if I click on the extrude view, you can see that all of the footing has been connected to each other, right? Right. So this is the first thing that I have connected this beam like this, but you can also connect that beam to this edge and passing from this edge. Both are similar and give you the same results, right? So this is the modeling of the step footing. And now the next step is to just run the analysis. And after running the analysis, you have to again click on the display and show the punching shear design. Now it is showing you not calculated. It means that the beam is not allowing any punching. NC means not calculated. It means there is no punching, right? So the punching issue is solved. So you can work with the 12-inch thickness by connecting all of the straight footing with the strap beam, right? So the first step was to define the strap beam, and take the depth of the beam equal to the thickness of the footing, which we did, and we took the depth 12 inches and width is equal to 15 inches, right? And then the next step is to check the punching, and there will be no issue, which we have seen there was no issue. And then you have to design the next step, and the important step in the step 14 design is the design of the beam as per ACI 31814, or you can use any version 31808 and 31804 19 and any version, right? Because the procedures and all the factors are the same, right? So the next step is to define this straight beam, because the design of this isolated footing is same in case of the isolated footing, in case of the step footing, but the new thing is here is the design of a straight beam, and it will be designed because some of the forces or stresses will be taken by these beams, right? So the just like for the slabs, there are also some recommendations or restriction from the ACI on the minimum on the maximum longitudinal reinforcements of the beam. And it says in section 9.6.1.2 that its minimum shall be of greater than A and B, right? So you have to calculate the A and B and these, and you have to select the greater value of A and B, right? So in our case, the H is 12 and D is 2.25. So if you import this in 3 into under root FC prime, and we are using FC prime 3000 and FY 60,000. So if you calculate it, it comes out to be 0.4 inch square. This is from the equation 1, right? And from the equation 2, it is 2000 divided by Fy into BD. BD is the width of the beam, right? This is 15 inches, and D is the depth of the beam. The effective depth of the beam, right? Not total H, right? This is D is equal to H minus 2.25. So if you insert all of these values in this equation B, it comes out to be 4.9. It comes out to be 0.49 inch square, right? So this is governs, right? So in the software, if the value is less than 0.49, you have to provide this much reinforcement. This is the minimum reinforcement, right? So let us go towards the safe. And let us design. This is the design of the beam. You can also check it from here, design, right? Display functioning, and you can also from here, but this is the quickest tool you can use for the design. You have to click on this show beam design, and it is, let us uncheck this impose minimum reinforcement and then click on apply, right? So let me show the, right? So now it is showing you the longitudinal reinforcement of the beam, right? So if I click on the impose minimum, so these values may increase, right? So let us check the required reinforcement for this beam, and we will take this beam, because you can see that there is a very much less bending moments as compared to these. So we will have a look at this beam. If you right click on this, so this will show you a report in which there are some the properties and the material properties and geometric properties of the beam, and it is showing you the length for which it has been designed, and these are the bending moments, and these are the reinforcements of the beam, right? So the top reinforcement A is, top means the area of steel at the top is 1.4 inch square, right? This is at the edge, and at the mid it is 0.6, and at this other corner this is 0, right? So no reinforcement is required at this corner. And the governing combo is this one, 1.232D plus 1.1 FY, all of these. And at the edge, there is no bottom reinforcement required. At the mid, there is no required, because it is taken by the top reinforcement. And the bottom reinforcement at this edge is 0.4864 inch square, right? So this is how you will read the report from the safe. So let us click on another beam, right? So this is now showing you different pattern, that the A stop at this edge is 0, at the mid is 0.5, and the other corner is 1.45, and the A's bottom at this edge is 0.5, mid and other corner it is 0, 0. Because the some bending moments are taken by the isolated footing, that is why it is uneven, just like the slab beam, right? So if I click on this beam, right, so it is now there is showing some 0, it is 0.17, and this is 0.07. This is because these are the required reinforcement, but you can see the bottom, it is showing you the at the left is 0.2 inch square and mid 0.23, and the right it is 0.3. But if I click on the imposed minimum, so this value will increase, right? So again, if I click on this beam, so now the required reinforcement is increased, and it is now showing you is 1.52, 0.66, and 0.03. So you have to select the maximum reinforcement, and you have to implement on all of the beam to make it very easy in the field as well as in the drafting, and you have to fulfill all of the requirements of the ACI, right? So the maximum we have seen at the top of the beam, the top reinforcement was 1.52, and you will check all of the beam one by one to select the maximum value. It is 1.34. So now it is 0.3, so this is very less. It is 0.5, it is 1.5. Now we are seeing that it's not working. These you can see that the blue lines, you can see these are the reinforcements, right? The tab is showing you these are the reinforcements, and you have to provide these reinforcements. So the bottom reinforcement is 0.34, and in other cases the bottom was because the maximum bending moment for the bottom is at the mid, and for the support it is at the edges. For the edge it was 1.52, and for the mid it was 0.34, right? So these are the maximum values right now. So you can also move the cursor over this beam, and you can see what is the value of, now it is the bottom, maximum bottom is 0.62, and at the top it is decreasing, right? But in some beams we have seen that the top was 1.52, right? You can see it is increasing to 1.42, and the bottom is in his here it is 0, right? So what we concluded that you will see the different beams, and you have to select the maximum value from it, and then we have to compare with the minimum requirement. So at the top it was 1.52 inch square, and at the bottom it was 0.62 inch square, right? And it is obvious that the bottom reinforcement is always less than the top reinforcement at the support, right? So this reinforcement is at the mid of the beam, and this is at the support of the beam, right? So the minimum requirement for the reinforcement was, according to ACI, is 0.49, and we are providing this much, so we are on the safe side. So now we have to use the reinforcements. So for this 1.52, if you use the number 4 bar, for example, it is 0.02, and if you divide that 1.52, it is, if you divide 1.52 divided by 0.2, so it comes out to be 7.6. So it means you have to provide 8 bars, 8 number 4 bars for the top, right? Only at the support, right? This is not the continuous bars. So you have to provide number 4 bars, 8, number 4 bars, 8 support, right? So we will talk about the how much reinforcement will be continuous, and right. So let us finalize this and then we'll move towards that. And for the bottom, we will be using again number 6 bar, number 4 bar, and we will dividing it with the area of the bar. 0.2 is the area of the number 4 bar, and this is the total reinforcement. So 3.1, so we will move upwards. So 4 bars is enough to transfer these loads. So we'll be using 4 number 4 bars, right? So this is the critical at the critical locations. The critical location for the top is support and for the bottom is mid, right? So how can we economize this, right? So let us go again to the safe, and we will check how much reinforcement is required at the mid for the top. You can see that there at the mid of the beam it is 0.66 almost, right? This much reinforcement should be continued, and this is very low. This is 0.64, this is 0.67, right? And here it is 0.82. So we will take the maximum value and we will imply the all of this. So the normally the average value is 0.62. So we will take, right? So this is top is equal to 0.65 inch square, and we will be using again this number 2 bar, and it will comes out to be 3.2. So we will select 4 bars. So it means that 4 bars will be continued throughout the beam, and we will provide extra 4 bar at the support. So we will be providing 4 number 3, 4 number 4 bars throughout. Throughout means continues. And these 4 extra bar will be provided only at the support, right? So this is for the top bars, and for the bottom bars we will see how much reinforcement is provided at the support, so we can continue this those reinforcements, right? So here it is showing me 0, and it is some portion is 0.11.
सर आवाज नहीं है।
अच्छा, अब आवाज आ रही?
जी।
अच्छा, कहाँ तक आपको मेरी आवाज खत्म हो गई थी, किस पोर्शन में? हेलो जी, कहाँ तक मेरी आवाज आ रही थी? उस मेरी आवाज खत्म हो गई थी कि वहां से मैं शुरू करूँ फिर?
पिछले 1 मिनट से आप स्टार्ट कर।
अच्छा, इट मीन्स के ये जो बॉटम रेनफोर्समेंट से जो हम एच पी देख रहे थे उस वहां तक, ठीक है? यहाँ तक हो गया था ये सब कुछ, यहाँ तक आवाज आ रही थी कि हमारी जो टॉप में कंटिन्यूस कितनी होगी?
हाँ जी सर, यहाँ तक आवाज आ रहा है।
Right, so this I was talking about the economy. If you want to, for example, we are getting bottom bars, number 4 bars at mid, this is the critical location, right? So if the uh, reinforcements are required less at the support for the bottom, because there is a very much less bending moment, so you can say negligible reinforcement required at the bottom. So we will see how many bars we can cut and save at the support, right? So for this you have to check the edges of the beams. So here the edge is asking the bottom reinforcement 0, and it is asking 0.08, it is asking 0.12, right? So this is 0.14, this is 0, this is 0.29, right? And now this is 0.37, and it is 0.22, and it is 0.4, and it is 0.11, right? So we have observed that at the support, the required bottom reinforcement is 0.4, right? So we will take the 0.4 inch square area and we will divide it with the point number 4 bar area, which is 0.2, and we will get 2 bars. So you have to provide continuous 2 bars for the bottoms, right? So to achieve the economy, you can cut 2 bars from these 4 bars and you have to provide only 2 bars at the mid of the beam, right? So we will be using number 4 bar, 2 number 4 bars throughout. Throughout means continue. So this is how you check the reinforcement for the beam in the safe and check the minimum requirement as per the code, right? So this was the whole story about the design of the beam. And now let us move towards the other requirement of the ACI, that is the maximum longitudinal reinforcement for the beam can be calculated using the ductility requirement as for the concrete strain is equal to 0.003 and strain in steel is 0.005. This is a long story and you can search in different literatures and books, right? And the equations are comes out to be this, right? So this is 0.271 into BW, the width of the beam. This is the effective depth, FC prime divided by Fy, right? So in our case, it is 0.71 into 15 into 9.75 and this, and it comes out to be 1.98 inch square. So this is the maximum limit. So you cannot provide an enforcement greater than this. So if the values are greater than this much, we have to increase the depth and width of the beam to justify or satisfy the this requirement of the ACI code, right? So the next step is again the design of the shear reinforcement for the beam. This was the previous story about the longitudinal reinforcement, and there is also a limit on the minimum reinforcement for the shear of the beam, and it is defined by the ACI 31814 in table 9.6.3.3, right? That if you are using non-pre-stress beams, which is our case, then the ACE minimum should be greater of this 0.75 under root FC prime PW divided by Fy. and BW is the width of the beam, and Fy is the steel yield strength, right? So in our case, it is 0.7 into square root 3000 into 15 is the width of the beam, and this is the Fy, and it comes out to be 0.01 inch square per inch. So if you want to calculate what type of reinforcement which we'll be using for the you can also calculate like this. I have calculated, for example, it is 0.11 is the area of number 3 bar. It is will be divided by 0.01 inch square per inch, and 12 comes out to be 11 inch square, 11 inch center to center, right? So this is how I calculated this, and it is not 13, it is actually 11. So number 3 bars at the rate 11 inches center to center. This is the minimum requirement. This is from the A, and from the B it is 50 into B. B is the actually the width of the beam, which is the 15, and we will do multiply with this 50. Into 15, and we will divide this by 60,000, and it is 0.0125, right? This is 0.0125, and if you use number 3 bar, so the area of the bar divided by the area required, and it is giving you 8.8 inch square per inch, right? So this is, you will go for the 8 inch center, right? So if the software, again, if it's giving you more reinforcement, so you have to provide at least minimum this much shear reinforcement for the beams, right? So let us start the next Zoom meeting. I will end this and we will start further from here, right?